right, so today what we're going to do is we're going to do part 2 of exponential decay. We've already talked about decay. We've talked about how it's different, but it's also similar to growth. We took 2 equations, we graphed them, we talked about how we can have vertical stretch or vertical shrink, we talked about the domain, we talked about the range. Then what we did was we took 2 graphs and we came up with equations for both growth and decay. When we look at growth and decay, notice that the equations, the essential equations, are very much the same. In fact, they are the same. The difference between a growth, however, is that the b itself. In a growth, it's greater than 1. In an exponential decay, it's a fraction or a decimal, right? When we do word problems with the decay model, notice that it's very similar to growth. I get y equals a parentheses 1 minus r parentheses to the t. A, we talked about the initial amount in the past for growth. This again is your starting value, what you're starting off with, and sometimes it can be money. The rate or the decay rate is R, it's a percentage. The decay factor, this is what makes it different. We're going to do 1 minus the rate. So for example, if I have 3% for a rate, I take it as 0.03, I turn it into a decimal. The decay factor, I take 1 minus 0.03. So that's what makes it a little bit different. It ends up being 0.97. Notice that it's between 0 and 1. T, the time period, is years. And so you'll notice how it's very similar to growth. However, we don't have it compounded, monthly, yearly, semi-annually. We do not have that with decay. Let's go ahead and look at a word problem. So, for example, the population of a city decreased from 1995 to 2003 by 1.5% annually. In 1995, there were about 357,000 people living in the city. Write a function that models the city's population since 1995. Then find the population of 2003. So notice that we're going to look at this population as declining. A lot of towns do this. Why is their population declining? What's going on with their town? How do you boost the population? Because again, you have more people living in your town, the more taxes you get, the more revenue is within your town, and the more it thrives. So first of all, we need to find the function, and then after that, we're going to find the population. So this is kind of a two-parter. So first of all, the first part, A, we're going to use the equation they gave us. Y equals A, parentheses 1 minus R to the T power. Right? And I'm going to put in P for Y because I'm trying to find the population. It said that it started in 1995 at 357,000. So 357,000, parentheses 1 minus the rate, you'll notice, is 1.5. So if I have a 1.5, I'm going to represent that as 0.015 as a decimal, and that's to the T power. Right? So this is my function. What makes it a function, again, is your input, which is T, and your P, which is your output. So when it asks for a function, this is what it's asking for. Now what we're going to do for part B is we're going to plug in how many years. So I'm going to take this same equation, P equals 357,000, 1 minus 0.015, and I got to find the T. Now you'll notice that it goes from 1995 to 2003. And so if I take those numbers, I'm going to end up getting 8. So that ends up being my T. And again, when you use this on your calculator, you're going to take 1 minus 0.015 equals, you're going to use your exponent key, which is generally like the caret key that we talked about before, to the 8th power equals, and then you're going to multiply it by 357,000. And so if you end up doing this math, you should end up with 316,342.88, right? And then we need to answer the question. I'm not going to have 0.88 people. So the population then is going to be approximately 316,343 people. So that's how many people are in this town after 8 years, if it continues to decrease. Okay. All right, so let's go on to the next problem. The next problem says the number of acres of ponderosa pine forest decreased in the United States, Western United States, from 1963 to 2002 by 0.5% annually. In 1963, there were about 41 million acres of ponderosa pine forests. They're going to ask us, first of all, to write a function that models this. So again, I am going to grab that equation, y equals a, parentheses, 1 minus r, parentheses to the t, right? I'm going to look at pine, the pine trees. So I'm going to go p equals, I'm going to look at how many were there, and it's 41 million. 41 million pine trees. So I'm going to put in 41. 1 minus, the rate is 0.05. So this is going to be 0.005, and it's going to be to the t power. Okay, so that is my function. Remember, we've talked about a function before. We have an input, we have an output. So it's going to be my equation. Part 2 now asks me to find out, to the nearest tenth, how many million of acres of ponderosa pine forest are there in 2002? So I'm going to take this equation again. All right, and I need to find out t. Well, first of all, it's from 1963 to 2002. So I'm going to take 2002. I'm going to subtract 1963, and I end up with 39. So that ends up being my t right here, right? I plug it into my calculator. P ends up giving me approximately 33.7, and that'll be million acres. Don't forget your label. Also, don't forget there are 2 parts to these word problems. First of all, to find a function. That's an equation. The second part then is to put in the number of years and find out how many of whatever there is. You're going to notice that with a decay, your numbers should get smaller. They shouldn't get bigger. So if they got bigger, you did something wrong, right? So make sure you're checking your answers as you are doing your assignment.